Okay, example 4. So in this case, I see that I have a sine expression on the top and on the bottom. So I'm going to work with these individually. So I have the limit as theta goes to 0. And in order to get the sine for theta to match my fundamental trig limit, I'm going to need to divide by 4 theta to get both the argument and the denominator to match. But if I put that on the bottom, then I also need to put it out the front so that I have not changed the expression. So this is just the same. I keep getting the wrong color, sorry. This is just the same here as multiplying by 1. And if I do the same thing on the bottom with my sine 3 theta, I can divide that by 3 theta, but then again, I need to multiply out the front by 3 theta. So hopefully you can see that we built two pieces that match my fundamental trig limit, one on the top and one on the bottom. And that leaves me with the limit as theta goes to 0 of, now I have 4 theta on 4 theta divided by 3 theta on 3 theta. And sorry, that's wrong, my bad. I have 4 theta on 3 theta because this piece has gone away and this piece has gone away. So I'm only left with 4 theta on 3 theta, and the thetas can cancel. So that just leaves me with 4/3. All right, example 5. When I look at example 5, I'm going to ask myself, will direct substitution work? Okay, so I believe direct substitution is going to work. So if I think about secant x is the same as 1 on cos x, and then cos of 0 would just be 1. So let's have a look at our little unit circle here. Okay, so this is equal to the limit as x goes to 0 of x times 1 on cos x. And what is cos 0? Cos 0 is 1, so I can plug in 0 for x. So x is 0, 1 on cos 0. Remember, at 0 radians, 2 pi radians, I'm looking for the x coordinate, that's 1. So I have 0 times 1 on 1, which is just 0. Okay, example 5. So when I tried direct substitution on this one, sine x, so sine of 0, if I look back on my previous diagram here, sine of 0 would be 0. So that would be a problem on this example 6. So then I have to ask myself, is there some sort of manipulation because I don't see the fundamental trig limit in this? So I'm going to go back to my trig identities. And that's how a lot of these limits might have to be algebraically manipulated if we don't see our fundamental trig limit. So tan, if you remember, is sine x on cos x. And that is being divided by sine x. In order to divide, we kiss and flip. So we have sine x on cos x multiplied by 1 on sine x. And I can see now that those sine x's are going to cancel. So that leaves me with the limit as x goes to 0 of 1 on cos x. And from example 5, we know that 1 on cos x is just going to be equal to 0 because when I substitute 0 in for the x value, cos of, sorry, not going to be equal to 0, it's going to be equal to 1. 1 on cos 0 is 1 on my unit circle. Okay, the x coordinate is 1. So 1 divided by 1 is equal to 1. All right, example 7. So here we are with another example. There's no sign in this, so it's not my fundamental trig limit. Okay, the fundamental trig limit only works with sine, not with cos. And when I look at this, I'm like, I can't use direct substitution. If I put 0 in, doesn't work because I get 0 in the denominator. I don't have any fractions to really work with. So one of the things I do notice is that cos theta minus 1, it might work to multiply this by its conjugate. So cos theta plus 1, what you do on the top, you need to do on the bottom, so you haven't changed the expression. That's all equal to 1. Okay, and so now I'm going to write the limit. Remember, you can't drop the limit part as theta goes to 0. Now, if you expand out that top, you get cos squared theta minus 1 when you FOIL it, multiplied by, I'm going to leave this in factored form, theta times cos theta plus 1. This is where you're going to need to know your identities. Okay, so if you think back to our Pythagorean identity, cos squared theta plus sine squared theta is equal to 1, and I want cos squared theta minus 1. So if I subtract the 1 to the left, then I'm going to subtract sine to the right. And so cos squared theta minus 1 is the same as negative sine squared theta. So I'm going to replace that. The limit as theta goes to 0 of negative sine squared theta divided by theta on cos theta plus 1. And now I'm starting to see I might actually be able to find a fundamental trig limit in this if I pull it apart a little. So the limit as theta goes to 0 of negative sine theta all divided by theta, and then I could have another sine theta left over cos theta plus 1. And then I hopefully have see, there's my fundamental trig limit. So he's going to equal to 1. And I'm going to rewrite this with what I have left over. Okay, so I have the limit as theta goes to 0 of negative sine theta on cos theta plus 1. And now I believe that we could use our direct substitution. Okay, so again, we're at 0 radians. And so the sine value at 0 radians is 0. So I have negative 0 on. The cos of 0 radians is 1. So negative 0 on 2 is just 0. Now this actually is another identity, or not identity, but another limit that's quite often seen. So the limit as theta approaches 0 of cos theta minus 1 on theta is equal to 0 is another good one to memorize if you're headed to doing more math at university. Okay, what's next? Example 8. So we're looking at the limit as x goes to infinity. So this is a little bit different than what we've been looking at so far. And then I have this x times sine on 1x. So it kind of looks like the fundamental trig limits. Maybe he's flipped upside down. I don't really like that x is going to infinity right now. So I'm going to do a different type of algebraic manipulation. I'm going to say, what if I let u equal to 1 on x? So let's look at this limit for a second. The limit, and I'll look at the variable that it's approaching in just a second. But so x, if u is equal to 1 on x, then x is going to be equal to 1 on u. And then I'm going to have that multiplied by sine u. Okay, now I have to look at this last little piece here. Okay, so if I think about as x approaches infinity, what's going to happen to u? well, then u is going to approach 1 on infinity. 1 on a very big number actually goes to 0. So it's going to be u approaches 0, which is exactly what I need over here for this to match my fundamental trig limit. So this could be written as the limit as u goes to 0 of sine u on u, and that, you guessed it, just equals to 1. So that's another different type of way that we can do our algebra. We could use a let statement, and as long as we get all our pieces to match up to our fundamental trig limit, then it's a new way of getting our answer to our limit. Okay, number 9. So this one looks really familiar to one that we did, really similar to one that we did a little earlier. So if I look at this, remember these little squaredy things just mean the whole thing is squared. So this is the limit as theta goes to 0 of sine 3 theta on sine 4 theta all squared. And I think you guys could probably figure this one out on your own. So if you wanted to pause the video at this point and give it a try, it wouldn't hurt. Okay, so this is equal to the limit as theta goes to 0 of sine 3 theta. Now I need a 3 theta on the bottom in order to get my fundamental trig limit, but to make this a true math expression staying the same, then I have a 3 theta on the top. And then this is all divided by sine 4 theta. And again, that in order to get to my fundamental trig limit, it's going to need a 4 theta on the bottom to get those two pieces to match. But I'll need a 4 theta at the top in order to keep my expression the same. And then this whole thing has been squared. All right, so let's think about this. Right here is my fundamental trig limit on the top, so that's going to go to 1. And then I have another one here on the bottom, so that also is going to go to 1. So that leaves me with the limit as theta goes to 0 of 3 theta on 4 theta all squared, and those thetas can cancel, so I'm left with 3 on 4 squared, which is 9 on 16. All right, number 10. Again, I think you could do this one without me, but if you need to see another example, direct substitution will work here. So I can go straight to not writing the limit out. Sine 0 plus 0, looking for my y coordinate on my x-axis at 0 radians is equal to 0. So this is just 0. 0 plus 0 equals to 0. All right, and example 11. Okay, I believe direct substitution will work on this one as well. So we have this is equal to sine pi plus cos pi. Now I'm over here at pi. The coordinates are -1 and 0. So sine of pi is the y coordinate, 0, plus cos pi is the x coordinate. So 0 plus -1 is just -1. Okay, and now I'm at number 12, which looks a little funky. I'm going to pause the video and I will start a new video for number 12. I'll see you back for video